And if you guys have questions or if you have specific problems you want to go over, let me know. And I'll make sure that if I don't get to it today, I'll make sure we get to it tomorrow and that we record it if you can't make it. Okay, so I posted a new assignment, assignment 5. I put the due date as Monday at midnight, but that was intended kind of as a soft due date because I want you to have this to be able to like practice on and be a little bit more prepared for the exam, and also and it's also kind of a little bit of a tease also because we're going to actually go through it and solve a lot of problems here. You'll have to redo it to get to the tables you need, the information you need, presumably, but at least you'll have a shot at knowing how to get started with the material. Okay, so let's read the first one. Most of these are confidence interval and related problems like hypothesis testing with the t-test. Okay, first one is random sample of Chinese assembly workers is surveyed, and for their weekly survey for their weekly salaries. The responses are reported in the data set called income underscore workers. They have an Excel version of that and a SPSS version of that, .sav. Find a 95% confidence interval for the average salary of the this population of workers. I'm going to go through that real quickly both ways. You know, if we were working individually, the way I would love to do this is to tell you, oh, you guys take a shot at this, and I'll look over your shoulder as you're doing it and like kind of steer you a bit. Unfortunately, that's kind of hard to do in this medium, but hopefully you get a chance. Even if you haven't done much with this before, after we go through with this, maybe you can forget about the lecture, this review, and try and do these problems on your own, so you're a little bit better prepared for them. So you actually teach yourself how to do them, and then if you get stuck and you need some help with it, you can always go back to the video and see that part of it. So I'm going to open up Excel. I'm going to open up that particular data file, which was called open. Let me go back to my desktop and date. I think it's in here. And head injuries, assembly workers' salaries. Okay, so we have, let's see, 30 less one at the top. We have 29 assembly workers whose salaries, weekly salaries, they don't make much. I don't even know what currencies these might be or whatever, but it's just a data set for us to work with. So we're asked for a confidence interval. Confidence intervals, this is a sample. So I can find the average of the sample, right? The average, or as we call it in statistics, the mean of the sample, easy enough, right? The average salary for this sample is $90 whatever it is and 24 cents per week. Okay, so that's easy enough to do, and we know that now. What we don't know is what the average salary is for all assembly line workers in China. And since this is a random sample, we make the assumption that our average for this random sample of 29 workers, that average sample approximates the mean of the entire population. In other words, mu, or the mean of the entire population. We will never know what mu is, because in order to know what mu is, we would have to survey every worker. We'd have to have data for every worker. They might have this kind of data, maybe not, but for our purposes, the only way we'll ever know mu, or the closest we'll ever get to knowing mu, is to know what the average for a random sample is. Now, problem is that we want to measure of how accurate, how much we can trust that average to accurately reflect the real average for the whole population. And that's where confidence interval comes in. Okay, so the way I'm going to calculate the confidence interval is I'm going to need to know what the standard deviation is for this population, and I'm going to use that with the sample size to determine the amount of variability I expect in these values. So now if I knew sigma, the standard deviation of the population, I would use that. Unfortunately, just like the mean of the population, I rarely ever get to know sigma. So the best that I can do, I'm just going to over here write in mean so we remember that's the mean. Okay, the best that I can do is calculate the standard deviation for the sample. So, okay, let's go ahead and calculate that. Equals STDEV, parentheses. I'm going to find standard deviation for this sample. And the standard deviation for the sample comes out to be about 21. So now I need to say to myself, well, if I took repeated samples of size 25, remember the sample size n is 29. If I took repeated samples of size 29, how variable would all of those means be? Because that's what really determines my confidence interval, not the standard deviation of the population, although indirectly it kind of influences it, but the standard deviation for all of those different, for all of the different means I would get if I took the sample over and over again at that size. And we call that special standard deviation, we call it the standard error. Oh, look at that. Standard error. I'm going to call it SE or standard error. Okay, so let me write that in just for good measure. Error. Okay, so the standard error is equal to the standard deviation divided by the square root of the sample size. Okay, and there's our standard error. Okay, now, because our standard error is based on the standard deviation of the sample rather than sigma, I'm going to have to be using something called a t-distribution instead of the standard normal distribution in z-scores. So I also I'm using the t-distribution because sample size is only 29. It's not big enough for me to assume that I know well enough to use the z-score. Okay, so now if I want to find the confidence interval, I know the confidence interval is going to be equal to x bar, which represents my mean, plus or minus. Well, now I have to decide what I'm going to multiply this by. How I'm going to create what's called the margin of error. Okay, so what we're subtracting and adding. Okay, so now if I knew sigma, or if the sample were large, I would use 1.96 because that represents a 95% confidence interval, or an alpha of 0.05 for a large sample, or for a situation where we know sigma, for normal distribution, in other words. Okay, so now I can't use 1.96. I have to use the equivalent for the t-distribution that's based on that sample size. So now that means I'm going to need to use my t-table. So I am going to go and look up my t-tables. Now, if I could have used 1.96 had I been in a situation where I knew that it was a very large sample, or I had that information. So I think I saved a copy of it here. I guess I didn't. I think it's called t-table. T-table. See if we can find it. Here we go. There's t-table. Okay, so for a sample size of 29, or in other words, 28 degrees of freedom, okay, my t-score, instead of being 1.96, because I have a certain amount of uncertainty because it's a small sample, it's going to be 2.048. Okay, so I'm going to go back to my Excel sheet. So it's going to be plus or minus 2.048 times the standard error. Okay, well, let's go ahead and calculate that. So it's going to be equal to the mean minus 2.048 times the standard error. There we are. Okay, and it's going to do the multiplication first and then the subtraction. So I think this should work okay. And sure enough, 82.25. Now I'm going to do my the upper limit for my confidence interval. It's going to be equal to x bar, the mean, plus 2.048 times the standard error, 3.89, and it comes out to 98. So we're 95% certain the true mean for this population is between 82.25, and I'll probably let you round this off to one decimal place, say 82.3 to 98.2. Okay, so our answer there, let me go back. Whoops, don't need that. Let me find it. Find a 95% confidence interval for the average salary. We just found it, correct? Now, what about the 99 and the 90% confidence interval, right? How do we calculate those? So I'm going to go back here. I'm going to say to myself, you know, if this is for my 99% confidence, 95% confidence interval. Having a little trouble there. Okay, this is my 95% confidence interval. I'm going to blow this up a bit more so we can actually see it. Okay, 95% confidence interval. So now if I want to repeat this for a 99% confidence interval, okay, well, let's see what I would do there. Okay, anybody know what number I would, 99% confidence interval. The only thing that would change here is we would be talking about X bar, right, plus or minus. Okay, and now because we're talking about a further out on the t distribution or the normal distribution, depending on whether we're using z or t, because we're going to be further out because we want to have more confidence. We want a smaller area that's outside of this area, smaller tails on either side. Anybody know for this? If I was using z, what would I be using for? Well, did I use the wrong number there? What is 2.38? What did I get wrong there? 2.58. Yeah, exactly. You beat me to it. 2.58. Thank you, Georgie. I would use 2.58 if I was using the z-square. I didn't even get the question out, did I? Okay, 2.58 if I were using the z-square. I use 2.58 times the standard error. But since I'm using the t-score, I have to go back again to my t-table. Let me see if I can't find it back there. There it is. And my t-table, for 99% confidence interval for my t-table, I would go down here to on this column to 28, and I would be using 2.763. I'm going to use 2.76 just to make it a little easier on myself. Okay, so I'm going to go back here. Whoops. 2.76 times the standard error. Now notice, because we're using a bigger number there, we're going to wind up creating a bigger margin of error. So we're going to be subtracting and adding a bigger number to my mean for the sample. So it's going to make my confidence interval wider. So you want to have a higher level of confidence, you have to make that interval wider. And this is the math of making it wider. So I'm going to say it's going to be equal to, actually, at this time I'm going to actually do something a little bit interesting. I'm going to use t, and I'm going to put 2.76 over there. Okay, so now I'm going to say, I'm going to calculate my 99% confidence interval. It's going to be equal to the mean, which is 90, minus 2.76 times times my standard error. There's my standard error. I'm going to hit enter, and that's, notice it's wider, 82. Now it's 79. And my upper limit is going to be equal to the mean plus 2.76 times my standard error. I'm going to hit enter. So that answer would be 79.5 to 101.0. Okay, so now watch this. What do I have to use if I want a 90% confidence in that I captured the mean? Well, now, since I'm willing to settle for less confidence in capturing the mean, it can be narrower. So it's going to be a smaller number. So let's go to T table. And if we were working with the z-score, it would be 1.64. But since we're working with the t-table, 90% confidence interval, in other words, a half 0.05 in each tail, there's two tails, 90%, okay, is going to be 28. It's going to be 1.7, 1.70. So I'm going to go back here. Now watch this. Because I did it this way, 1.70, since I referenced that cell as my t-score, I can now just change that. When I hit enter, it's automatically going to update my confidence interval. So now it should become narrower. And there it is. It's narrower than my 99% confidence interval and it's also narrower than my 95% confidence interval, 83.6 to 96.9. Okay, so I mean that's how we would deal with that. The only curve that you're likely to run into there is if it's a large sample, you can use Z, and if it's also if you know the population standard deviation, you can use C. Okay, so I'll move on to the next problem. The heights of randomly selected college students is measured and the data is collected in the file heights.xls and heights.sav. Report the average female height in this sample in the 95% confidence interval for heights. Report the average male height in this sample in 95% confidence interval. Test to determine if the average male height in this population is significantly larger than the female height with an alpha of 0.05 with a tolerance for error of 0.05. Provide a null hypothesis, report the value of t and the p-value, p being the probability of being wrong if you reject the null hypothesis, the area under the tails, and report your conclusions, report regard to the null hypothesis. Can you reject it or not? Okay, so let's take a look at this. We're on a 95% confidence interval. Well, one way, we actually use two-tail for both. If you go back to the, excuse me, that's a good question. If you go back here, okay, if you go back here, the 99% confidence interval, that's 1% error, but there's actually only 0.5% in the right tail. Oh, you know what it is? They mention, I understand what you're saying now. They call it right tail probability. So at 99% confidence interval, the right tail, the probability, the area of the right tail is 0.5%. But by definition, in order to get 99% confidence interval, you also have to include the left tail, which is 0.05. They could have said right and left tail probability, or both, each 0.05, and then added them together. Fun. It's kind of like, it's kind of a little tricky the way that they phrased that there. So, all right, so all of these, if you look at all of these, they refer to the right tail probability, and it's always half of what the alpha is. 80%, it's 10% in each tail, though. You know, not just the right tail, but the left tail also. So again, I would have called that left or right tail probability. Okay, so let me go back here. So I'm going to open up that data set. Okay, I'm going to close this one. I'm not going to save this. Actually, I'll leave it open for a second. Open. Okay, now I'm going to get the test data. And we're looking for height down here. Okay, so I'm going to open this up. And we got a little bit of a twist here. 0, I think, is females, 1 is male, and so on and so forth. So what I could do is I could sort this data in Excel, right? I'll just show you how that's done right now. Okay, I'm going to just take all of that, highlight both rows. I can go up to data, sort, and I can tell that I want it to sort by gender, which is these 0s and 1s. And since these are both highlighted together, okay, I didn't include the header, so I'm going to uncheck that. I'm going to click OK. And now it's sorted it so that all the female heights, I'm not sure which one is which, all the female heights and all the male heights are separated, so you can work with them separately. Now, you could do this just the way, find the 95% confidence intervals, just the way I did before, which was to do the calculation in Excel, as we did before, calculate standard deviations, standard error, and so on and so forth. But we can save an awful lot of time by using SPSS instead. So I'm going to open this same file in SPSS. Okay. Okay, as it bounces up and down, eventually it'll open. Here we go. Okay, I'm going to cancel that. I'm going to say open data. And I'll navigate myself up to the desktop. and the test data. And it's only showing me the SAV files because it says that right there. Okay, so I'm going to open up that heights file. It's going to be the same numbers. It's going to be broken up into male and female now. Now, if I remember correctly, I think I coded this. Oh, I didn't code it for you. Oh my goodness. Okay, I'm going to have to go back and code it. So for now, I'm going to, I'm not even going to bother. I would say that 0 represents female and 1 represents male, except I'm not sure which of those it is. So I'm not going to code it right now, just going to leave it 1s and 2s so that we can go through this problem. So first, I want to know what the 95% confidence interval is for males and for females. So I'm going to go up to Analyze. Now I'm going to do something wrong here to start off with, just so you see that what the problem is. I'm going to go into Descriptive Statistics, Descriptives, and I'm going to ask it for the average height. Now, there's nowhere to put gender here, right? So I'm going to click OK. Now, it's going to calculate the average height for me, but it doesn't give me the confidence interval. And not only that, it's the average height for everybody in the survey, not the average for males or females. So in order to find the average for males or females, you have to go down a little further, go to Analyze, Descriptive Statistics, Explore. And we go into here, and now we have a place where we can factor this into 2 groups. So I'm going to move the heights into the dependence list. I'm going to move gender into the factor list. By factor means to break up into different parts. And so we have 2, it's going to break up by male and female. So I'm going to click in statistics, and it's already going to set up to find the confidence interval for a 95% confidence interval. If we had asked you to find a 99% confidence interval, I would change this to 99%. So SPSS would give us that instead. So I'm going to click OK. And SPSS is going to calculate many statistics for these 2 groups, including for each group. For each group, it's going to calculate, let's see, the mean is 70.9. The mean for the zeros is 70.9. Mean for the ones is 65.4. So which one's the males now? So I can tell now the ones are the males. I'm actually going to go in here now to my data file. I'm going to go into variable view. I'm going to go ahead and code this while I'm at it. Okay, so I can upload it later on when we're done. 0 represents male, and 1 represents female. I'm going to click OK, and I'm going to go back to my data view. And if I turn on value labels, it'll show me what each one of them is. Still a 1, still technically, still really a 1 and 0, but now SPSS can show us what it is. So I'm going to do this again. Descriptive Statistics Explore. It's already set up, so I'm going to just click OK. And when the output comes up now it says male 70.9. The confidence interval 70.4 and 71.45. Female confidence interval 64.9, almost 65. This is 65.8. So we have confidence interval and mean as we were asked for before. So now we want to do a hypothesis test to test test whether the means for these 2 groups, males and females, the heights, are the same or different. Well, we know it's going to be different, likely to be different. However, we want to know if this data gives us sufficient information to say with 95% certainty, with less than 5% chance of being wrong, that we've actually proved that now, that our results are statistically significant. So I'm going to go into, first I'm going to write my null hypothesis. Okay, and my null hypothesis, H null, is that the mean height for males is equal to the mean height for females. And my alternative hypothesis is the mean height for males does not equal the mean height for females. Notice it doesn't tell it. We're not testing to see if the males or females are taller or shorter. We're going to be happy with just proving that they're different. For now, that's a 2-sided test. A lot of times you'll work with 2-sided, even though you're looking for a difference in one direction, you'll do a 2-sided test anyway, because you don't have a justification for knowing for sure it's going to be that direction with the particular sample that you took, and also because it's a more conservative test. So in order to avoid being wrong or doing the bad kind of error, type 1 error, you might just stick with a two-sided test unless they specifically ask for a one-sided test. Let's go back and do our t-test. The way we would do a t-test is that we would remember those formulas that we had. If we were doing it in Excel, we would find the standard deviation. We would find the means of the two groups. We would set up t is equal to, let me just write it down here. T is equal to x bar 1 minus x bar 2, the difference between the two means, divided by the standard error. And how would the standard error be calculated? Well, we have formulas for calculating the standard error when we have a two-sample t-test like this. And those formulas are based on what the two standard deviations are and what the sample size is, right? Except that depending on whether the standard deviations of these two groups are similar or very different, we have a different set of formulas that we would use. Okay, so if you go back, you'll see that in previous classes and in the class notes, we had a chart with those formulas in it. You can fill it in. If we assume that they're equal to standard deviations, it's a fairly simple calculation. If we assume that they're different, this calculation for standard deviation, for standard error, is also pretty simple. However, the calculating the degrees of freedom, if we assume that they're different, can get pretty complicated. And we can get very weird numbers. So when we work with different standard deviations, when they're drastically different standard deviations, very frequently what we'll do for degrees of freedom, just take the smaller sample size of the two groups and subtract 1. Okay, so now I'm going to use SPSS to do this instead. So let me go back to SPSS, if I can get there, and I'm going to go ahead and do a t-test in SPSS. So I'm going to go to Analyze, Descriptive Statistics, no. Compare means, yes, we're comparing means. So it's not a one sample test. One sample test, we would have a single sample comparing it to a known value for another population, a known population mean, for instance. Independent samples t-test, well, that sounds right. They're independent samples. They're not paired samples, they're independent samples. We'll talk about paired samples in a second. So I'm going to click independent samples. I'm going to move the test variable height into there and the grouping variable into here. That's going to ask me to define the groups. And I'm going to, you might remember it was 0 and 1 for male and female. And then I'm going to click, let's see, make sure it's 95%. It is. And I'm going to click OK. And SPSS calculates the mean, standard deviation, standard error for the two groups, and so on. Okay, so now SPSS does the calculations we would have done in Excel. It calculates the t-score, the degrees of freedom. It calculates the standard error for a pooled standard error. In other words, equal variances, and it calculates a different standard error if you assume the variances are different, right? So that's why those two numbers are different there. Now, which of these two rows should we use? Well, the way we decide which of these two rows, equal variance is assumed, equal variance is not assumed, is that we start with the assumption that the variances are equal, just like null hypothesis, that things are the same, equal variances are assumed. And if these four boxes represent a calculation for the probability that you would be wrong if you reject the idea of equal variances, right? So we want this significance, this p-value, this probability of being wrong, to be less than 0.05 in order to reject the idea of equal variances. Since it's not less than 0.05, we stay with the top row. We fail to say that equal variances assumed is wrong, so we assume that it is right. We stay with it. So t is equal to, that's the difference in the two means, that real big, nice big number. The degrees of freedom is equal to the sum of the two groups minus 2. Okay, n1 plus n2 minus 2. If you add these two up, it's going to come out to 379. You subtract 2 is 377. So this probability of being wrong if you reject your null hypothesis that the two means are equal is less than 0.001. Okay, so that means that there's very little chance we would be wrong if we reject the null hypothesis, that this is well under 0.05. So We reject the null hypothesis. Remember, the null hypothesis is what this was all about. We reject the null hypothesis and we accept the alternative hypothesis. Now, what if we had used, what if this had been less than 0.05? We would have used the bottom line. We still would have rejected the null hypothesis, right? Would have been a slightly different t-score. It would have been a different standard error, and so on and so forth. But as it happens, in this case, the outcome overall is going to be the same. Okay, so let's move on to the next problem. And I'm going to save this. Okay, save. Okay, I'm going to get that out of the way. So next problem, the problem number 3. Struggling students are tested before and after tutoring sessions. Results for these tests are saved in the files testresultstutors.sav. Most students show an improvement in their test scores, but the test sample is very small. I think it's only 9 or 10. We'll take a look at it in a second. Perform a hypothesis test to determine if there is a significant difference in the performance on the tests after tutoring. Alpha is equal to 0.01. Oh, well, wait a second. We want a 99% certainty that we're right before we reject the null hypothesis, right? Rather than a 95. So let's put in our null hypothesis here. H null is that there's no significant difference in performance. In other words, the mu1, the test score, average test score for mu1 minus the average test score for mu2 is equal to 0. There's no difference between the two. And our alternative hypothesis is that mu1 minus mu2 does not equal 0. Okay, get the idea now. This is going to be a little bit clearer if I open up the Excel file so you can see what this data looks like. I'm going to say open. Okay, where am I here? And let's see, student. Test results, there we go. Okay, so let's take a look at it in Excel. Okay, so here are the test results. Okay, in these test results, this person had their test score was 110. After tutoring, it was 120. Before it was 96. After it was 90, 105. There's 1 or 2 people where it goes down. 120 went down to 118, and so on. But we want to know if we got enough evidence here. It's 10 people, right? Well, because it's the thing that makes it a paired sample is that this isn't one group of people and this is second group of people, right? This is the performance for one person, participant 1. Before it was 110, after it was 120. Before he was 96, after this guy was 105. So really what we're interested in is the difference between after and before. This person went up 10, this next person went up, so on and so forth. Okay, so I'm gonna copy this calculation down. So these are the differences. We don't want to know if these differences are big enough from this small sample to say with 95% certainty, that 99% certainty, that we can say that these differences, the average difference for if we did it for many whole population would not be 0. So now that we've found this difference, we don't have to worry about these numbers anymore. We're only interested in the difference. So this is essentially a one sample t-test. In other words, we're going to calculate, this is going to be our average, and we're going to see if our t-score is big enough to reject our null hypothesis. And how do we do that? T is equal to the average we get for this minus the average that we think for the null group, which is 0. So it's just going to be the average of this divided by the standard error. And you would calculate standard error based on the variability and the standard deviation of these numbers. And you would go for a sample size of 9, you would use the t-value for sample size of 9 to calculate your confidence interval or for your calculating your standard error and so on. Okay, so I'm going to actually do this in SPSS now. Again, SPSS is a good way to do it. Even if you like using Excel, it's a good way to do it because it's a good way to check your answer as well if you do it in Excel. So I'm going to open the data file, open data. We go into test results. Okay, and here's our test results. Participant 1, before, after, and so on and so forth. And I'm going to go into analyze. I'm comparing the means still, right? The means that he's before and after. So I'm going to compare means, except this time I'm working with paired samples. So I'm going to click on that. Well, since it's paired samples, SPSS wants to put in the two variables that we're working with. Well, the first variable I'm working with is before, and the second variable I'm working with is the score after. So I'm going to say, and I'm going to go up to options. And now, remember, we wanted it for 99%. Alpha is equal to 0.01. We wanted to see if our significance is less than 0.01, less than 1% chance of being wrong. So I'm going to click continue. I'm going to click OK. And let's see what SPSS gives us for this. Well, since it's not really two samples, it's really the difference it's analyzing, it doesn't give us two lines because it's only got a single sample. So there's not two possibilities for equal or different standard deviations. So let's see, the average difference between before and after is 17.2. I put before first and after second. If you put after first and before second, it would have come out to be a positive 17.2, but it effectively doesn't mean anything for our analysis. So here's the standard deviation for those 10 people. Here's the standard error based on the t-score that we need and the standard deviation, okay, and the sample size. What's the 99% confidence interval for the difference? This is it. I'm going to come back to that in a second. But the t-score for the difference is minus 3.36. Our t-score is 3.36. 9 degrees of freedom. That gives us a two-tailed significance. In other words, the total of the area of both sides. One side's 0.04, the other side's 0.004, the other side's 0.004. Added together, they're 0.008, which is less than 0.01, right? 0.010. So, what do we do? Can we reject the null hypothesis? Opinions out there? Can I reject the null hypothesis as a 99% confidence or alpha is equal to 0.01 level? I don't think so. I think we can reject it. The reason why I say we can reject it is because the probability of being wrong, this two-tailed significance, is less than 1%. If this is less than alpha, which is 1% in our case this time, then we can reject the null hypothesis. I'll show you another clue to knowing whether or not we can reject the null hypothesis. Look at the 99% confidence interval of the differences. Okay, it's negative 1/2 up to negative 33. So we're 99% sure that the real difference is between negative 1/2 and negative 33. So we're also 99% sure that since 0 is not inside of that range, it's not a positive number, a negative number, where we can be 99% sure that it's not 0. The difference is not 0. So our null hypothesis was that the difference between the two groups was 0. So both the confidence, 99% confidence interval, and this very small significance both tell us we can reject the null hypothesis. Okay, does that make sense? Are you comfortable with that? Okay, good. All right, that's the key here, is whether or not this number is less than, in our case now, 0.01, or usually less than 0.05, but because I demanded a little bit more accuracy, 0.01. Okay, so let's take a look at the next problem. 4 patients in 3 types of medical facilities are randomly sampled and a pulmonary function test performs. The results are summarized in an Excel file and an SPSS file. Perform a hypothesis test to determine that if there's a difference between pulmonary function tests for patients in hospitals versus rehab centers. I'm going to go through this real quick because it's basically the same as the other problems that we were working with. Okay, so if I look at this, I'm going to open. I'm not going to open Excel. I'm just going to go straight to SPSS. I'm going to say open data function test. Okay, and here's we have private hospitals and we have public hospitals, and we're comparing whether or not the patients in one or the other are in worse shape based on their pulmonary function test. So our null hypothesis is that the mean pulmonary FEV test for private hospital patients is equal to the mean pulmonary function test, FEV test, for public hospital patients. And our alternative is that they're different. Okay, let me just read that a little bit more carefully. Different. Yep, if there's a difference. Doesn't say test if one is more than the other, just says if there's a difference. So that's a two-sided test. So I'm going to go up to Analyze, compare means. It's an independent samples t-test again. Okay, and I'm going to, let's see, FEV1 is the numerical variable. I'm going to put it into test variable, and the center or type of hospital goes into the grouping variable. Now, the only problem is I don't remember if that was ones and twos, or let me change the, let me turn off the value labels. That's ones and twos. Okay, so define the groups. There's one, and there's two, public and private. Okay, I'm going to click OK. And let's see what we wind up with. Again, SPSS performs the analysis. It finds the mean of each group, standard deviation, and so on and so forth. And now it actually does the t-test. So now this box tells us whether or not to use the top or the bottom line. Okay, equal variance, we're going to start with that assumed. Is this less than 0.05? No, it's not. So we can't reject equal variance as assumed. We're going to stay with the top line. I'm going to go across the t-score is 0.47, and the significance is 0.64. Can I reject the null hypothesis here? If my significance is 0.64, my alpha is 0.05. Nope, again, you reject your significance, this is your probability of being wrong if you reject the null hypothesis. So in other words, your chances of being wrong if you reject the null hypothesis here is 64%. You want this number to be less than 5%, less than 0.05. Okay, so we have to make sure that we understand that this one is the probability of being wrong if you say I reject the null hypothesis. That's a type 1 error. We want to avoid those. So we say, so in this case, since our chances of being wrong, remember, look how big how small the t-score is. That's because there's a very small difference between the two means. So because there's a very small difference between the two means, they're so close together, the likelihood that I would be able to reject the null hypothesis is pretty low anyway. And as it turns out, the t-score, based on the difference between these two, is very small, and the probability of being wrong is very large, 64%. So in order to reject the null hypothesis, your significance calculate, or just in other words, we call this the p-value, the significance, the probability of wrong if you reject the null hypothesis. The probability of wrong is 64%, 0.64. We failed to reject the null hypothesis. We don't say we failed to reject the null hypothesis and accept the alternative hypothesis. We just say we failed to reject the null hypothesis. Right. Well, remember, alpha is based on our level of confidence that we want. Alpha, if we want to be 95% sure, alpha is 5%. Being 95% certain is the same thing as having 5% chance of being wrong. Being 99% certain, like in the previous problem, is the same thing as saying I'm willing to accept 1% chance of being, only 1% chance of being wrong. So in this case, alpha is 0.05. Previous problem, alpha was 0.01. So we had to get a result, a significance or a p-value less than, in this case, 0.05, or in the previous case, less than 0.01. In this case, we did not, 0.05. In this case, we did not get a result less than 0.05. In the previous case, we wanted to be 99% certain, so our tolerance for error was only 1%. But it wound up that our significance, our probability of being wrong, turned out to be less than 1%, or 0.01. So in this case, we failed to reject. In this case, even though it's more rigorous, we need an even smaller significance. We did get a small significance, so we reject in this case. We failed to reject in this case. Okay, so the next two problems are based on chi-square. So I'm going to save those for tomorrow, and in the meantime, give this a try and see how it works out for you, and hopefully you'll be able to. If you have struggle with it, go back to the video. I'll try and post it as quickly as I can, so you guys can use it as a guide if you need to. Okay, so if you can make it tomorrow, great. If not, I'll see you guys on Monday. But you'll hear me on the video if you catch the video after I record it. Okay, so good night, guys. Have a good Saturday evening. See you guys. Good night.